Good evening.
Good evening.
Are you able to see the screen?
Yes, sir.
Yes, sir. Yes, sir.
Okay. I think in the last class we have talked about crystallographic directions, right?
Yes, sir.
Okay, so when we are talking about crystallographic directions, we have just quickly reiterate what we have done. So let us say you have 100, 110, 111. So the method to look at this is to basically identify from the origin, you have to draw the vector with these projections into x, y, z axis, right? So as a result, 100 will be along that direction. 110, x projection is 1, y projection is 1, that is this point. So this will be my 110, and x projection 1, y projection 1, z projection 1, right? That will be my 111 point, 111 vector. Okay. So if you look at this fellow, we have written how the Miller indices should be written for the indices to be written. For example, if you look at this fellow, what is the x-intercept? It is intersecting
1
x
by
at
2.
a by 2. So
Point.
1 by 2, a by 2, y is intersected at b, z 0. So instead of a by 2, b 0, we will write 1 half, 1, 0. But we don't represent these numbers in fractions. So you multiply with some common factor so that the lowest integer it is reduced to. So if you multiply with 2, then this becomes 1, 2, and 0. Then this direction will be 1, 2, 0. Okay. And when if you have to represent a crystallographic direction, you put a bracket, square bracket. And we also have learned in cubic crystals, any permutation of these three symbols will be equivalent directions. So all such, the family of crystallographic directions, the family of equivalent crystallographic directions are represented by these brackets, right? Angle brackets. So for example, when you say 100 family, all permutations of these three symbols, 1, 1 and 2 zeros and their negative counterparts will form the family of equivalent directions as far as cubic crystals are concerned. So these permutations work only for cubic crystals. Keep that in mind. And we have also discussed how to do that for hexagonal crystals. And we have seen that if I use 3-index system, then the concept of equivalent directions being represented by permutations does not work. And hence we have introduced a 4-index notation. And with the 4-index notation, that permutation seems to work. Okay, but I would not spend much time on, if you did not understand hexagonal crystal system, that is fine. As long as you understand that the directions can be represented in a cubic crystal in this way. Okay, now we will move on to representing the crystallographic planes. Is there any question until now?
No, sir.
No questions. Okay, good. What is the total cost class strength?
Sir, for 23 batch, we have 23 people, sir.
And about others, the 24 batch?
We have 25, sir. Around 25 we have class time.
Yeah, so we should get 49 people, right? Only 32 people have joined, which includes me and my presentation as well as the studio guy.
Sir, here at Mahendra, we have
Sir,
time.
Sir, here
Uh-huh.
in Mahindra, we have a sit together, sir. 9 people are sit together.
Okay.
Okay.
Got it. Okay. So now let us look at the crystallographic planes representation using crystallographic planes. Okay. Sorry, representation of crystallographic planes. So the orientation of plane is described similar to the directions, and whatever indices that we are using for representing point, direction, and now we are going to deal with the planes. These indices are called Miller indices. They are named after a crystallographer called Miller, and hence they are called Miller indices. For a plane, these indices are represented by H, K, and L in a parenthesis. So the point that I would like you to recognize is the following. If you are representing points, there are no enclosures. If you are representing a direction, the direction is represented by a square enclosure, and a family of directions are represented by an angular enclosure, and a plane is represented by a parenthesis as an enclosure. A family of planes will be represented by curly braces. We will see that. Okay. And any two parallel planes are always equivalent and have identical indices. If you have two parallel planes, they have same index. We will see how. So now how do we go about determining these indices H, K, and L? What we need to do is, first we need to see if the plane passes through the origin of the lattice. Okay. If the plane, you have to check if the plane is passing through the origin of the lattice, the origin of the unit cell that you have chosen. If it is passing through, then you should choose either another parallel plane or you change your origin. So the requirement is the plane must not pass through origin. If at all a plane is passing through the origin, all that you need to do is you change your origin. And then with respect to that origin, you describe the plane, or you choose another parallel plane within the unit cell, which will also have same indices. Okay.
Professor sir, can you just
Yeah.
explain it by little diagrammic
I
drawing
will explain. First, I want to explain verbose so that you see the difficulty. Then I will explain through.
thank you, sir.
That is the idea. Okay.
Thank you, sir. Thank you.
So when you have a plane which is intersecting or passing through the origin, you need to move the plane. Okay. And at this point, once you are moving the plane away from the origin, that means it is not passing through the origin, then the plane in that situation will either intersect the coordinate axis or it will become parallel to the coordinate axis. Only one of these two should happen because the plane is not passing through origin. If it is passing through origin, it is possible that it is not touching any of the coordinate axis. Now what we are saying is the plane must not pass through origin, and as a result your plane, after changing your origin, either it will intersect coordinate axis or it will become parallel to the coordinate axis. If at all it is intersecting the coordinate axis, then you record the length of the intercept, like what you have done for the directions also. And then you take the reciprocals of those numbers. Suppose if you take a plane that is parallel to an axis, then what is the length of the intercept?
No intersect actually.
No intercept. That means we can say that intercept is at infinity. Can we say that intercept is at infinity because it is not touching the plane?
Yes, we can.
Can I?
Yes.
So once you note down those intercepts, you prepare the reciprocals of those numbers. So since a plane parallel to an axis is considered to be intersecting at infinity, that reciprocal will be 0. Okay. And then again, scale the indices to nearest integers and collect them as HKL. So much for verbose. Let us look at how it should be done in reality. So a crystallographic plane is represented by HKL and with parenthesis, a family of crystallographic planes are permutations of HK and L with curly braces. In cubic system, the planes having same indices regardless of the order are equivalent. Okay, forget about hexagonal crystal system. Now you look at this fellow. Now this is your unit cell with your A, B, C as your lattice parameters. Now you look at this yellow guy. Is this guy passing through origin? First you need to check whether the plane is passing through origin or not.
Yes, sir.
It is passing through origin. So what we should do as per the guideline?
Should move it.
The origin should be chosen to be differently. So instead of choosing origin here, can I choose origin here?
Yes, sir.
Yes,
Then
yes,
it
we
will
can.
not pass through origin, isn't it?
Yes, sir.
If I am taking my origin here, that triad is moving this way. That means this is negative x direction, negative y direction, x direction and g direction. Okay. So now what I have done is instead of moving my origin, I moved my unit cell like that. Either way is fine. So this is my origin O dash x dash y z dash y. That is my origin now. Now what do I need to do? Next step, I need to identify the intercepts. Isn't it? Is this plane intersecting x-axis? This is x-axis. This was original x-axis, but this is now moved x-axis because the plane should not move through origin. Is this plane anywhere cutting the x-axis?
No, it is
No.
parallel.
It is parallel. So x-intercept is infinity. What is y-intercept? Where is it intersecting y-axis? Minus b. So can I say minus 1? It is intersecting z-axis at 1/2. So
1/2, yeah.
so it is x-axis is parallel, so it is infinity.
Minus
Y-axis
one.
minus 1. Z-axis is 1/2. Correct?
So the reason why we'll take reciprocal itself is because of infinity coming in place. That's the reason.
Exactly. So then you take the infinity, the reciprocal is 0, 1, 2. Now, when you took the reciprocal, you see that there is no need for reduction, right? Because there is no need for common multiplier because all of them are integers now. Otherwise, you need to multiply with some number, isn't it?
Yes, sir.
So now your enclosure, you put the enclosure and this is 0, 1 bar 2. So the index for this plane is 0, 1 bar 2. Miller index for that plane. Is that clear?
Yes, sir.
Yes, sir.
Okay, good. So now I would like you to construct this plane. You try on your own. 0, 2 bar 1. Just look at the steps that we have taken before. You have to go backwards, right? Because this is what you have, 0, 2 bar 1. So if you want to find the intercept, what you should do?
Reciprocal we need to find.
You should take the reciprocals. The reciprocals are the intercepts, isn't it?
So it will not like cut x-axis anywhere.
So it will be parallel to x-axis.
Yeah.
And it is cutting y-axis at
2.
Negative
2 or
half.
minus 2.
Minus 2.
No, it is cutting at minus 1 by 2, not minus 2.
Negative half. Yeah.
Okay, sorry.
Negative
Because
of
reciprocal, we have to take,
reciprocal of that.
yeah.
And z-axis?
Same one.
Z-axis is 1. So how does that plane look like? Can you draw?
Minus 2, 1 by 2.
Minus 1.
Huh?
Outside the box from the left side.
That is B. That is minus B by 2. Right? Z. And it is parallel to x-axis. Are you able to see that?
Yes, sir.
Now I would like you to plot 110 plane.
Zero.
110.
Covering A, B, area, AB square. Covering A, B.
Sir, bottom plane, sir.
Bottom plane.
The face on
Bottom-
the XY, the face on the XY plane.
Yeah. 110 will be, let me draw it.
Corner, this corner.
Shaded portion.
So
So
inside
it should be 45 degree
Z-axis,
inclined to like O axis and yeah.
By 2 and by 2 0.
That is my 110 plane, isn't it?
10 plane. Okay.
110, not 10.
110. Okay.
Settled 0.
ಇಲ್ಲ, zero.
Yeah, it will not touch
No, not
that
bad.
Z axis anywhere. Yeah.
Parallel. So it's not cutting at all, not touching at all.
This plane is parallel to z-axis. No, it is not intersecting z-axis.
Yeah.
Correct.
Hmm?
Understood, sir.
Understood, sir.
Okay. Now can you plot 111 plane?
Top corner.
Where it is 45 degree means it's joining from 0 to
Diagonal
Diagonal.
to
0 to that. Yeah.
This place, this point, na?
That point, sir. Yeah.
X, Y, and Z.
That is my 111 plane. Are you able to see that?
Sir,
Hmm?
Right, sir. Right. Yeah.
1 bar 1.
It will just mirror image of this, sir. Simple. Like XY plane का mirror ले लेंगे तो बन जाएगा. If I'm not wrong.
Mirror about Z axis.
Mirror about that axis.
1 bar 1. 1 bar is y negative I am putting.
Yes, sir. So mirror about Z axis.
So please draw all of them.
Mirror about XY, XZ plane.
correct.
Yes, sir.
Yeah, done?
Yeah, yes, sir.
Okay. Now let me share my screen. 1 minute. Are you seeing my screen now?
Yes,
Sir,
sir.
it is blurred actually.
Yeah, now is it
It's
okay?
coming now. Yeah.
Yes, sir.
Because I wanted to write it on the screen. Okay. So this plane we have done. So 0, 2 bar 1 you have constructed. And now if you look at this fellow, what is this plane by the way? What is the Miller index of that plane?
110.
110.
110.
110, sir.
1 minus 1.
All three of them should have same index. All parallel planes will have same index.
-1, -1, -1. No, -1.
So let us say this is my origin. Okay.
Okay.
That is my x,
-1.
that is my y, that is z.
Sir.
So now I have to write the Miller indices for that plane. Where is it cutting x-axis?
1,
One.
-1, -1.
1.
Is it cutting
No,
x-axis?
it is
plane?
parallel.
No, it's parallel to.
It's parallel, but okay.
So it is parallel to x-axis. So it is cutting x-axis at infinity. Avoid y-axis.
Oh, okay.
Again, infinity.
0, 0,
minus
1.
Z-axis
It's -1.
minus 1. So reciprocals are 1 by infinity is 0, 0, 1 bar.
0, 0, 1 bar.
0, 0, 1 bar. And how about this guy?
0, 0, 1.
0, 0, 1.
0, 0.
So this is actually 0, 0, 1. Not comma should not be there. The plane is all parallel planes should have same index.
HK.
How about this guy?
That's the one we drew that time, right? The
Yeah.
42
What is
degree.
it? We drew, but now we should say
110.
1, 1.
110.
110, yeah.
And how about this fellow?
111.
1, 1, 1.
111, yeah.
Okay, good. So if you are looking at a cubic system, oops. I'm sorry for that. So yeah. I'm sorry that I now let us look at this guy. This blue color plane, is it clear to all of you that it is 0, 0, 1?
Yeah, yes, sir.
Yes, sir, of course.
There is no question, right?
Yeah.
And it turns out that in a cubic system, the indices of a plane and the normal to the plane will be same. It is only true for cubic system. You can verify that. Because this direction is 0, 0, 1 is something that we know, right? Is that direction 0, 0, 1 or not?
Z-axis, yeah.
Yeah. So in a cubic system, the plane and directions will be with same indices.
Input inverse it will be same, yeah.
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 That is true only for cubic systems. For other systems, it need not be true, but we will be dealing with mostly cubic systems. That is why we are making this observation. Okay. And if I say in future 0, 0, 1 and a cubic crystal represented by this, meaning I am talking about this plane and that direction. By looking at the enclosures, you should be able to find out what am I referring to. Correct?
Yes, sir.
All right. So this is a very important observation as far as cubic systems are concerned. Now, we come to the actual reason why we have learnt about these crystallographic directions and crystallographic planes. As I told you, the equivalent crystallographic directions will simply be permutations of those symbols. Similarly, equivalent crystallographic planes in cubic system will also be permutations of those symbols, which basically means that if I am talking about 1, 1, 1 plane is equivalent to 1 bar 1, 1 or 1, 1 bar 1 or 1 bar 1 bar 1, all of them are equivalent. Okay. You should keep that in mind. Now, let us define a very important quantity called linear density. Okay. So how do I define linear density? Linear density is nothing but number of atoms centered on a direction vector divided by the length of the direction vector. What do I mean by that? Suppose if I take this crystal lattice, this is the unit cell that I am interested in. Okay. In this unit cell, I am looking at that direction. What is the direction, by the way? Is it clear that that is 110 direction?
Yes, sir.
Yes, sir. Along XY plane,
No.
therefore 0 is on Z.
110. So there is no ambiguity whatsoever, right?
Yeah.
Now, along that direction, we define something called linear density, meaning how many number of atoms effectively are centered on the direction vector divided by the length of the direction vector. If it is a cubic crystal, we know that this is equal to A, and A, isn't it?
Yeah.
Yeah.
What type of a crystal is this? What type of a unit cell is this?
FCC.
FCC, face-centered cubic cell, right?
Yes, sir.
Now, if I look at 110 direction, if you draw these circles larger, these atoms will touch each other at along this direction. But if you look at these two atoms do not touch, but only along these directions is touch depending on the geometry that we have. Now, if you look at this direction vector or this lattice vector or crystallographic direction, you will see that effectively this atom, half of that atom is on the direction vector and half of this atom, and this full atom is sitting on the direction vector. Do you agree?
Yeah, yeah.
Yes, sir.
So effectively, how many number of atoms are centered on this vector?
2 atoms.
2
2 atoms. What is the length of the vector?
root 2.
So this is A square root 2 A. So that means root 2 by A is the linear density. Isn't it?
Square root of A.
a square plus a square, sorry, x square is equal to a square plus
A
a
square
square,
plus.
right?
So 2A.
That is equal to 2a square, x square.
Yeah.
X is equal to root 2a.
Yeah.
Yeah, it should be root 2A, right, sir?
Yeah. But if you are writing in terms of radius of atom,
2R.
no, 4r. Because this is 2r.
4R, 4R.
Along
Yeah, yeah,
the
4R,
diagonal
4R.
So
Yeah, yeah.
root 2 by 4r. And please note that that means here what we are saying is root 2a is equal to 4r, isn't it?
Yes.
This is true for what? For an FCC crystal.
FCC.
That means the radius of atom is root 2a by 4, right? Or a by 2 root.
A by 2 root.
That is the radius of the atom. Now linear density is because you have two atoms centered around that divided by 4 times r, that is 1 by 2 r. That is my linear density of what? 110 direction. Linear density of 110 direction is that 1 by 2 r or root 2 by a, or all of you agree with that? Is that clear? Is there any question
Yeah.
there?
Sir, if it is cubic, will it actually vary along different directions, the linear density?
Let us check. If you take 110, 100,
It is different.
Yeah.
LD 100 is different or not?
Yeah, yeah.
But how about LD 101?
That is same.
What is that one? How do I draw that vector?
Perpendicular.
This is 110. How do I draw 101?
Along the left face. Yeah.
Is that 101?
Yeah, yeah.
Yeah. Yes, sir.
That will also have same or not?
Yes.
Yeah, sir.
That is why these are called equivalent directions. Along equivalent directions, although they are not parallel directions, they will have same linear density. That is why they are equivalent directions. Okay?
Noted, sir.
Yeah.
Sir, 111 will have a unique direction, right? That is different.
Yeah,
Yeah,
111 is what?
Diagonal.
Yeah.
So
Diagonal
you try
point,
to
yeah.
find out what is the density on along 111 direction. Okay?
It should also be same, sir, if I'm not wrong.
Why?
Because
What is the distance?
They will not touch
Okay,
also,
okay.
right?
Okay. So
It will not be
basically,
same, no? Because
it will not be
it's body
same. It will be
diagonal.
higher. It will be higher. It will be higher.
Body
Sorry.
diagonal.
It is body diagonal, no?
Yeah, yeah.
If it is body diagonal, are there any atoms in the center of the thing?
No.
No, it is
It'll
not
be
BC.
empty.
It's not BCC.
It's not BCC, it is FCC.
Yeah.
So the linear density on 110 direction in FCC is 1 by 2r, but that will not be same in BCC.
Yeah.
In BCC, these two guys will be touching. Isn't it?
Yes, yes, yes.
So the crystallographic direction, linear density will depend on the crystal structure. LD110 on an FCC lattice is this much. It is not same as in the BCC lattice on the same direction. Okay? And it turns out that in FCC material, this is 110 direction is most closely packed direction. 1 minute, I have to take this call. Hello. Sorry, yeah, sorry for that. Now, so that is so much for the what do you call the linear, the directional dependent properties. Now we have defined crystallographic planes, right? So now let us look at another quantity called planar density. Okay. So the planar density, the definition itself is number of atoms centered on a plane. In the linear density, you have to take the length of the vector. Because it is a planar density, you have to take the area of the plane. So the unit for linear density is per meter. For unit for planar density is per meter square. Okay, you have to be very careful. Now, if you take FCC lattice, what is this plane, by the way? What plane is this? What is the Miller indices for this plane?
110.
110. So we are trying to find out the planar density for this particular plane. If you look at this planar density, so this is the picture that you will get. So how many atoms are effectively there in this plane by looking at this picture?
6.
6.
6, sir.
2
Half becomes what?
2 atom.
Centered na vandu
1.
2,
And
3,
this
4,
one? 1/4,
4.
1/4, 1/4, 1/4.
4.
So total how many? 2 into 1/2 plus
4 into 1/4.
1/4. Effectively,
Plus
2
1, 2.
atoms.
2 atoms are only there.
Sama.
What is the area? Again, if it is A, this is root 2A. And what is this length?
That is A.
A, right? So 2 by root 2A square, right? Is that correct?
Yeah, yes, sir.
Yes, sir.
So root 2 by A square. That is the planar density. What is A and R relation?
R equal to root 2A by 4.
What did we derive previously? R is equal to A by 2 root 2. Correct? Or A is equal to 2 root 2 R. Isn't it? So what did I say? My planar density is root 2 by A square. Root 2, A is what? 2 root 2 R. So 2 root 2 square R square, that is root 2 by 4 times 2 R square, 8 R square. Right? And 1 by 4 root 2 R square. That is what we have. Isn't it?
Yeah.
So this
Yes,
is the planar density of 110 plane in an FCC lattice. Yeah, is there a question?
No, sir, we are clear.
Yeah. So now can you find out the planar density of 100 plane? I want to know planar density for 100 plane. That means I am thinking of this plane, isn't it? Is that the plane that I am looking for?
Yes, sir.
Is that the one?
One x-axis
No, that is Y.
perpendicular.
What is that plane, by the way?
That is basically Y. 0, 1, 0.
0, 1, 0.
0, 1, 0.
Very good. I am looking for this plane.
That one.
So I am actually looking for this plane. Right? How many atoms are there?
Quarter 1,
2 atoms.
2.
Why 2?
1 FCC dana.
Center one.
Center ஒன்னு இருக்குல்ல?
Two
So
atoms.
one whole atom and 4 quarters.
Yes.
Okay.
One whole atom plus 1/4. So 4 into 1 by 4 plus 1. That is 2 atoms. What is the area?
A square.
A square. 2 by A square. Which one has higher density? 110 or 100?
110.
Hmm?
இல்ல இல்ல இதுக்கு ஏரியா அதுக்கு கூட இதுக்கு ஏரியா கம்மி. So இதுதான் டென்சிட்டி கூட.
110.
110. Okay. Why 110?
So 0 and 0, right?
010 sir. இல்ல
110 only, no?
110 only.
He's comparing between 110 and 100.
PD of 110 is how much? Root 2
Root 2
by A square.
square.
PD of 100 is how much?
2 by A square. 2 by A square is
Definitely
higher.
2 by A square is
2 by
higher.
A square is higher.
So which one has higher planar density?
100.
100. Can you find out the planar density of 111?
ஒன்னு அப்படியே அங்க B ஓட கனெக்ட் ஆகும்.
111 means I am looking
B.
for this plane.
The triangle.
Triangle.
Atom connect ஆகும்.
இது மூணு சேர்ந்து ஒரு ஆட்டம், கீழே ஒரு ஆட்டம், ரெண்டு ஆட்டம்.
இது யாரா இது யாரா ஒண்ணு.
இல்ல சார், மூணு குவார்டரும் சேர்ந்து ஒரு ஆட்டம் சார். சென்டர்ல இருக்கு, நடுவுல ஆட்டமே இல்ல, ஒரு ஆட்டம் தான். டோட்டல் ஒன் ஆட்டம் தான். ஆமா.
இதுல எதுவும் வரும் இல்லையா? 1/3 வரும்ல. இது 1/3 1/3 1/3
1/3 1/3 1/3 அதனால ஒரு ஆட்டம்.
என்ன சைடு பண்ணது
half v என்னது லென்த் தானே, half into v into h தானே.
ஃப்ரீ சென்டர்ட் ஒன்னு இருக்குது. பண்ணுவோம்.
அது
பேஸ் சென்டர்ட் இல்ல. அதான் √2 a. ஓ சாரி.
I hope everyone is trying to do.
Yes.
Sir, so 1.5 say 1.5 அது ஒரு 2.5 atoms.
இல்ல 1.5 ஆட்டம்.
இது அரை, அது ஒரு அரை, கீழே ஒரு அரை.
1.5 தான்.
1.5 தான் சார்.
1/2 yes இருக்குடா.
அதுக்கப்புறம் 3 1/3
1/3 into 3
ஆ.
plus
1.2
1/2
1.2
into 1.
இந்த பாதி பேர் இதுல பாதி
அது 1/4 yes இருக்குடா.
இது இல்லையா?
அது செட் ஆகுது.
நல்ல டச் ஆகுது.
அப்ப எவ்வளவு டச்
E மட்டும் தான். E நோட் போட்டுருக்கு.
E ஆஃப், இது ஒரு 1.
No, no. See, in the 111 plane,
எதுரா?
3 corner atoms into 1/6. Plus 3 side atoms into 1/2.
It root to A. To H என்னது? H வந்து A.
ஏலாம் சார்.
டாப்.
அது ஏக்குறது.
Sir, I have one doubt actually in the previous question actually. Yeah, why are we dividing the corner atoms by 4 actually? 4 into 1/4 we put, right? Actually, it should be 4 into 1/8, right? Actually.
Why 1/8? Yeah, tell me.
Because there will be one layer will be adjacent to the four elements will be coming in the same plane. 4 cubes. There is one more cube in the top or bottom. There'll be another 4, right? Actually, there'll be 8. Will be sharing that single atom, right?
You
Is
draw
my
the
understanding correct?
neighbors, so there will be one more guy here, right?
Yeah, right.
There will be one more guy.
Yeah.
And this guy is one more.
Yeah.
Right? and this guy is one more. What else?
Yeah, in the forward side also there will be 4 more cubes, same like another face in the forward.
Yeah. Yeah.
So in that case, there are 8 cubes are sharing 1 atoms, right?
So we have done a calculation mistake, isn't it?
No. I'm just trying to understand how are we sharing by 1 by 4.
So no, what you are saying is correct. That's what I wanted to get to. Because when you do the 111, you will get the clarity.
Okay.
So let me show you the 111 scenario. This is the 111 plane. When you increase the size of these atoms until they touch, this is the 111 plane. This is how 111 plane look like. Okay. So then if you draw the plane, only 1/6 of that plane is occupied by that fellow. And 1/2 of that, 1/2 of that. This is also 1/2 of that. So 3 into 1/2 plus 3 into 1/6. 3 into 1/2 is 3.5 plus half. So total 4 atoms. Okay. So depending upon the orientation, so what you are looking at is total, if you cut that plane, if you cut a plane, what is the amount of area available is what we are looking at when we are drawing that the plane. Right here we are not taking half. It is not about centering how much. So this area that is participating in this plane is what we are looking for. Right? That is 1/6 of the total area. And because it's a triangle, you have to, what type of a triangle is this?
Isosceles.
Equilateral.
Is it isosceles or
equilateral.
equilateral?
Equilateral, sorry.
Equilateral.
Sir,
Equilateral.
Equilateral
Sir.
triangle. So
Sir.
if you know A, then you can find out the area of that fellow. Right?
Sir, atoms. Hello.
Yeah.
So total atoms will be 3 by 2, 3 into 1 by 2 will be
1.5.
1.5 will be, sir.
3 into 1
by 2
2
is 1.5
1.5.
plus 0.5.
so 3 into 1 by 2 is 1.5 plus
plus 0.5. 0.5 is 2.
0.5. That is, sorry, 2 atoms. Not 2, 4. There should be 2 atoms. You are right. Effectively 2 atoms. That is correct. And with this 4 and that this 4 goes to the numerator. 2 and 2 gets cancelled. So you have 4 by root 3a square, or it is in this term. And you will see for an FCC crystal, you will see that PD111 is the highest. And this is the most closely packed plane. Okay. So why we are interested in linear density and planar density? Because the knowledge of linear and planar density is extremely important for us to understand the deformation mechanisms. We will talk about slip in crystalline materials in the next module. That is where we need to understand the reason for certain deformation procedures, and that is strongly dependent on the crystal structure. And the type of deformation will be revealed, the mechanism underlying the deformation will be revealed by knowing the values of linear density and planar density. And what will be more interesting to know is that which is the most closely packed plane in a crystal and what are the closely packed directions. In an FCC crystal, what is the most closely packed plane?
111.
Closely packed direction?
0, 1.
Meaning, when I say most closely packed plane, I am looking for PD highest.
Highest.
And when I say most closely packed direction, I am looking for LD highest.
Okay.
So This
by
is
square.
closely packed plane. This is my closely packed
Direction.
direction. So typically, when we want to understand the the crystal deformation on a crystalline materials, it is very important that we have the information about most closely packed planes and closely packed directions. Okay. So in a FCC material, we have seen what is the most closely packed direction. 110 direction, isn't it?
Yeah. Yeah.
Similarly, what is the most closely packed plane? You will see, you can compare and you will see that it is 110 direction, 111 direction, 111, not 110. So in FCC is most closely packed plane and is most closely packed direction. Is that clear? Any questions here?
Clear, sir.
Yeah, good. So if you look at what are the materials that are FCC structures, several metals like gold, copper, aluminum, silver, lead, tin, platinum, gamma iron, these have FCC crystal structure. For you to remember easily, these are metals that are easily deformable. They all have FCC crystal structure. Until now, I have shown only points at the lattice points. But now if you, this is what we call a ball stick model, wherein the atoms at the lattice points are taken in such a way that at least two atoms in the lattice will be touching each other. Here in an FCC, you will see that these guys are touching and these two guys are not touching. Right? This is the first plane of atoms. The green one is the second plane. Red one is the third plane. You have three planes of atoms put together, one over the other, three stacks. Okay. And that gives you your FCC structure. And when you add these things in, when you take this unit cell, stack it in X, Y, and Z directions, you will get a crystal lattice like that. Okay. If you want to understand a little bit more on this, I encourage you to go through these videos. I have already uploaded them in the portal. You can have a look at it and please watch these videos. They give much more deeper insight into the crystal, how a particular fraction of the crystal should be taken in calculating linear density and planar density. So far we have looked at two things. One-dimensional quantity for representing a crystal is a linear density by crystallographic direction vector, and a two-dimensional quantity is an area which is represented by a crystallographic plane. Now if you come to three-dimensional representation, three-dimensional measure, then we will define something called packing density. It's very important. What is atomic packing density? If you take this FCC crystal, there are some atoms in a particular crystal lattice. You calculate the volume of atoms in the unit cell divided by the unit cell volume. What do I mean by that? If you look at this fellow, how many atoms are there in this particular unit cell? How many atoms are there?
Oh,
14.
3 items.
14 atoms. Effectively, how many are there?
3 items.
Three atoms.
Why?
3 atoms.
Why?
The
How many
blue and
faces
red
are
are
there?
shared by
No, how many faces are there?
6.
6 faces.
Each face has a face-centered atom
Yes.
that is shared by how many unit cells?
2.
Right. Say 2.
2.
That itself is 3, right? And each corner atom is shared by?
8.
8.
So, how many corners are there?
4
Eight.
corners.
8 corners.
8 into 1 by 8 is 1. So, total 4
Four.
atoms are there in an FCC unit cell. We have seen that already earlier we have discussed this. Effectively, there are 4 atoms, right? And what is the
Yes,
volume
sir.
of each of those atoms? If the atom radius is pi r, the volume of those atoms is 4/3 pi r cube, isn't it? Into
Yes.
4. Do you agree?
Yes, sir.
Yes.
What is the, suppose if you take this as my unit cell, so let me draw the unit cell for you. That is the unit cell space occupied by this fellow, right? What is this? This is A, that is A, that is A. What is A is equal to what in terms of R?
2
2 root 2 R.
2 root r. Yeah.
So A is equal to 2 root 2 R. So volume of this unit cell will be A cube. That means the space occupied by the unit cell is A cube, isn't it?
Yes,
Do you
sir.
agree?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
That is 16 root 2 R cube. All of you agree?
Yes, sir.
So what is packing density? Total volume occupied by the atoms, that is 16 pi R cube by 3 into volume occupied by the unit cell, that is 16 root 2 R cube. 16 gets cancelled, R cube gets cancelled. Then what you have is pi by
3.
3 root 2.
3 root. Can you calculate what is pi by 3 root 2?
Point 1
740.
1.12.
0.740, sir.
0.740. If you have to write it in percentage,
74%.
74%, right?
Highest.
That is what it is. An FCC crystal, no matter what, it can only occupy 74% of volume. A similar thing can we do for BCC? So a BCC lattice looks like this, something like that. Okay, you have, what is the effective number of atoms in a BCC?
2.
1 plus 1 by 8 into 8, 2. What is the volume?
A cube, sir.
Volume is A cube, but what is A in terms of, so what is the 2 into 4/3 pi r cube is your volume. This volume also should be written in terms of A, no?
That is
A is 4r by root 3 because body diagonal is 4r for this fellow.
Yes. A root 3 by 4. R is equal to A root 3 by 4. Therefore,
R is equal to root 3a by 4 or A is equal
Correct.
to 4r by root 3.
R
So
by root 3.
4r by root 3 whole cube, isn't it?
Yes.
So 2 into 4 pi r cube into root 3 into 3 divided by 4 cube r cube. R cube gets cancelled. 4 square, that is equal to 2 pi 6 root 3 pi divided by 16. Is that correct? No. Yeah. There is something wrong I have done. Okay. Eight pi r cube by 3 into 4 cube R cube by root 3 into 3 because root 3 cube. 3 gets cancelled. R cube gets cancelled. That is equal to 8 pi root 3 by 4 into 4 into 4. 16, that is 2. So pi root 3 by 8. What is that?
இது
0.68.
So that is 68%. So that is the volume occupied by, that is the atomic packing density of a BCC unit cell.
root 2 ஏவா the length equal to root 2 correct?
So the point that here is the volume. So FCC, you will see that amongst all the crystal structures, FCC is the most densely packed system and BCC is not that much. You can also compute for simple cubic.
correct?
You will also realize that
The length
the
என்ன
packing
சொல்லுது?
density for HCP is also
The
74.
இந்த length கரெக்டா? இதுதான் இங்க வரைஞ்சிருக்கோம். இது
HCP
என்னது?
also 74. Okay.
A இது. அப்படின்னா இந்த length என்ன? root 2a. root 2a. கரெக்டா? root 2a தான் இங்க போட்டிருக்கோம். root 2a root 2a. So இந்த length என்ன? Square root of root 2a whole square plus a square. 2a square plus a square. இது என்ன போ? 3a தான்.
Any other questions?
Clear, sir. Clear.
Clear, right?
Yes, sir.
So HCP also will have same crystal structure, same packing density you can calculate. But there is one more thing that I wanted to talk about. In a three-dimensional state, not only the packing density, there is something else that is very important, is called coordination number. What is the meaning of coordination number? The meaning of coordination number is the following. The meaning of coordination number is how many nearest neighbors are there for each atom in the crystal structure. Okay. So now let us look at this fellow. How many nearest neighbors are there for this fellow? Or one corner atom we will take. So the number of nearest neighbors are 12. That means this guy has a coordination number of 12. For BCC, you can take the central atom. The central atom is touching all the corner points. So it has 8. How many corner atoms are there? 8 corner atoms are there.
8.
So its coordination number will be 8. For FCC, you please verify that it is 12 yourself. You go back and then look at that video, and then that becomes very clear to you. Okay.
Okay.
So now we define something called theoretical density of a material. Suppose if you take copper, one can find the atomic radius of copper to be 0.128 nanometers. And atomic weight of copper is 63.5 gram per mole. That means 1 mole of copper, if you take, it weighs 63.5 grams. Do you understand what is the meaning of 1 mole? 1 mole of any substance will have 6.023 into 10 power 24 atoms, or if substance is an element, it will have 6.023 into 10 power 24 atoms. 23, sorry. Power 23. That is the meaning of that. So if you take 1 mole of that substance, for example, copper, it will weigh, that means 6.023 into 10 power 23 atoms of copper will weigh 63.5 grams. That is the meaning of atomic weight. Okay? For 1 mole, it will weigh 63.5 grams. Now, density of copper. What is density? Mass per unit volume, right? So, this basically tells you the density of any material is given by number of atoms associated with the unit cell. Per unit cell, how many atoms are there? Into atomic weight. Right, what it will tell you? Number of atoms. Atomic weight is gram per mole. Right? Number of atoms in a unit cell. But what is the, you are looking at a unit cell, so you have to take unit cell volume. What you need to find out? Mass of the number of atoms. You have number of atoms, you have the atomic mass. So you have to multiply with 1 mole is equal to how many number of atoms? 1 mole is 6.023 into 10 power 24, right? So if you carefully look at it, you have number of atoms into atomic weight is units gram per mole. Volume of unit cell is meter cube. I could write in terms of meter cube. But 1 mole is how much? Number of atoms into grams divided by 6.023 into 10 power 23 atoms, 1 mole into meter cube, number of atoms. This is cancelled and you will get gram per meter cube. That is your mass unit for density. That is what this formula is. Number of atoms per unit cell times atomic weight. So basically atomic weight by Avogadro's number. This is what we call 6.023 into 10 power 23 is your Avogadro's number. That will give you the total, the mass of 6.023 into 10 power 24 atoms, right? But the number of atoms per atom mass it will give you. This will give you atom per, mass per atom. Mass per atom into number of atoms will give you total mass of the atoms there are there. So this gives you total mass of the atoms, and this is the volume in that unit cell. That is our theoretical density. Is that clear? Yeah, is it clear?
Yes, sir.
Okay. So now let us calculate the theoretical density of copper. Can you please calculate? If it is given, how many number of atoms are there per unit cell in a copper unit cell? Copper will be having what kind of crystal structure?
FCC.
FCC.
Four.
So how many
Four.
atoms are there per unit cell in FCC?
4.
4 into 63.5 divided by what is the volume of the unit cell?
A cube. So
Huh?
basically
4 by root 3.
In terms of radius, no, atom radius is known. A
4 by
cube
root 3.
A cube.
is
Therefore,
2 root 2 r whole cube, right?
yeah.
A 2 root 2 r whole cube or 2 root 2 r only, no?
Yes, sir.
R cube.
8 into 2, that is 16.
R2 root 2 R cube.
16 root 2 R cube. That is 16 times root 2 times 0.128 into 10 power minus 9 whole cube. Why minus 9? Because it's in nanometers. Grams, so I am converting it to kg, 10 power minus 3. Okay, 6.023 into 10 power 23. So this is minus 27 plus 23 will become 10 power 4 when it goes up. That cancels with 10 power minus 3 becomes 10. So it becomes 4 into 63.5 into 10 divided by 16 into root 2 into 6.023 into 0.128 cube. That's what I have. And that will be my density of copper. Isn't it? Can you calculate what will be the density of copper using that?
One seven three five seven grams per meter cube. 17357.453 grams per meter cube.
So kg per meter cube or gram per cc. That is, they are the standard, no?
Then 17.35 kg per meter cube.
Yeah. So can you do a Google search and find out what is the density of copper?
$8.9.
It's 8.94 gram per cm cube.
But what you are getting?
We are getting lower because it's
Why?
theoretical.
Why are you getting
Because of
lower?
Impurities, voids, imperfections.
But theoretical density is what you have searched for, no? You have not searched for anything. So let us say your radius is 0.128 nanometers, right? Atomic weight is 63.5 gram per mole. That is 63.5 into 10 power minus 3 kg. Number of atoms is 4 or 8?
4 is FCC.
4, sir, FCC.
So density is number of atoms into atomic weight, right? Divided by volume. What is the volume? 2 root 2. 2 root 2 r, isn't it?
Yes.
That is the A. Correct? I am getting 8,887 theoretical density. How come you are getting 7,000? I am getting 8,887 kg per meter cube. Someone did a wrong calculation. Or I might have done some wrong calculation in the equations. I have directly calculated using calculator.
887 is only coming, sir. 887.
Okay. So that is close to what you have it in the internet, right? So that is how the theoretical density of any material is computed. All right. So in the next 10 minutes, we will quickly see how to develop these closed packed structures. So let us say you have 3 layers. So first you have kept in this fashion the closed packed plane. This is a closed packed plane where atoms are sitting at positions, centers A positions. Can you see that? And then next set of atoms are kept on above this at filling B positions like that. And then still you can see there is a gap here, right? You can see through these holes. And the next level, you put it at the C. So that means what you have done is, first you have created layer A, then layer B, layer C. What is layer A? Where you are keeping your atoms in closed packed fashion. And then you are moving it and putting it on the next plane. And then moving it and putting it on the next plane. And like that, you are creating a 3-dimensional structure. So if you stack the atoms, the closed packed atoms as ABC, ABC, ABC layers. So what you are doing is like this. AB, if you look, you can create 2 kinds of layers, right? ABC, 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 or maybe to make vertically, if you want to see, it will be A, B, C, A, B, C, like that. That's how you are creating out of plane. Instead of doing that ABC, ABC, if you do AB, 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 both of them are closed packed configurations. It is just that the way that you are stacking them is different. And if you stack them in this fashion, then you get an FCC crystal. If you stack them in this fashion, then you get an HCP crystal. Both of them are closed packed, and hence you will see that their packing fraction is 74%. Okay, this is your HCP. A, B, A, B, A, B. Like that, you will have infinitely packed. Whereas in FCC, you will have A, B, C, A, B, C. So 3 layers. So if you look at these 3 guys, that is what I have shown you here. This is the layer A. Blue color is layer A. Green color is layer B. Red color is layer C. So that is how the FCC crystal is stacked. And now you can see different, from there you can create an FCC crystal and you can cut it in different planes and look at it. Now, what might happen in general, you have to create this, when you are creating this crystal, you have to create this stacking, right? ABC, 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 like that. In all, infinitely. For a perfect crystal, the stacking should happen. Sometimes what might happen is, there may be some mistakes. Meaning, some false creeping, in which one of the A lattice is missing, A layer is missing. That means first layer is A, B, C. Next you should actually put an A layer. But if that is missing and next comes a BC layer, then that is what called a stacking fault. Normally it should have been ABC, ABC, ABC. And now you see that the layer A is missing here. But afterwards it continued. So this is what we call a stacking fault. And this is one of the ways that you can have your crystals having not a perfect crystal. And because of this, what happens is the crystal's energy will increase. That is what we call a stacking fault energy. You need not know the details at this point of time because our focus is not on understanding these details, but know that you can have these mistakes that are happening. These are called stacking fault energies, stacking faults. Now, as we have discussed, in a crystal, you have a unit cell. Now let us look at a two-dimensional scenario. I am not talking about a three-dimensional crystal. Let us look at two-dimensional crystal. In a two-dimensional crystal, let us say this is my unit cell. Now, if I arrange my unit cells like that, then I get a crystal, right? All of you agree with that? Yeah?
Yes, sir.
Good. Now, let me try to do the following. You're able to see my screen, right? So, let me try this first. So, this is your material, and here I am looking at it. And in this domain, my crystal unit cells are stacked like that. And it will continue like that throughout the system. If you fill in this space with this by stacking them in that direction, that is how you will fill the space, and then you get a crystal. But sometimes what might happen is this is one set of unit cells coming together, but this, what is basic building block of this crystal? Carefully, if I look at it, that is the basic building block of that crystal. If I isolate that, let me see. That is my basic building block. That is my unit cell. All of you agree with that?
Yes, sir.
Yes, sir. Yes, sir.
Now, instead of having that guy, I have a, for some reason, I have a rotated one. Okay. So again, but the unit cell is the same, it just got rotated. The orientation of this guy is different from this guy. So when I see this fellow and this fellow, now there is an incompatibility. So this guy wants to be like that, and this guy wants to be like that. Isn't it? The unit cell coming from this fellow, the unit cell coming from this fellow, when they are meeting, there is an incompatibility. Can you see that?
Yes, sir.
Yes,
Yes,
sir.
sir.
So if you have some incompatibility like that, this is what happens in all the most of the materials. So I can see this as a grain, this as another grain. Basically meaning a grain is collection of unit cells oriented in a particular fashion. A grain 1, grain 2. They have two different orientations. Similarly, I can have another grain, that is grain 3. This can be grain 4. Each grain may have its own orientation. In that particular grain, all the unit cells are oriented in a specific direction, but the adjacent grain has a different orientation. Okay. So, such a crystal is what we call a polycrystalline material. What so far we have, if you have a crystal in which all unit cells are oriented in the same fashion, that means you will have only one grain, because there is no incompatibility between adjacent grains, because all the unit cells are arranged in the single orientation. Then such a crystal is called single crystal material. In general, most of the material that we deal with are polycrystalline materials, but we will also deal with single crystal material. What is a single crystal material? In that particular crystal, all the atoms are oriented in this, all the unit cells are oriented in a specific direction. There is no incompatibility when these unit cells are trying to one particular, if you come from two different directions, the unit cells will not see any incompatibility anywhere they meet. Whereas in a polycrystalline material, wherever the unit cell orientations are differing, then they will see an incompatibility. And that is the primary difference between a single crystal material and a polycrystalline material. Okay. So that is precisely what I am talking about. This is a grain 1, grain 2, grain 3, grain 4, grain 5, grain 6, grain 7. So each one of them can be represented by something called a grain boundary, which is basically talking about the incompatibility between them. Most of the materials are polycrystalline in nature, and sometimes we may have to deal with single crystal materials, which can offer some special properties for engineering application. Okay, and this is important that we understand the existence of single crystalline and polycrystalline materials. Okay, and we also should understand what is a non-crystalline material. So this is a long range order, right? If this long range order is lost, then that becomes a non-crystalline material. But a polycrystalline material will have long range order within a grain, but across the grains you will lose that long range order. But if you rotate it, again you will see an order. But in a non-crystalline material, no order exists at any level. That means even within a grain, you will not have materials oriented in a specific long range order. Okay? Any questions here?
No, clear, sir. Clear, sir.
So one quick question. So does
Yes.
this same as grain direction?
Sorry?
So while machining, grain directions will be an important factor. Does this
Grain orientation.
Yeah,
You're right.
yeah.
Yes. So
okay,
that
sir.
is because that happens. We will talk about it when you are rolling a material. No, if you take a rod and roll the rod, then grains will be elongated along the rolling direction. Then the material will develop some strength in a specific direction. The material will become anisotropic by nature. So then your grain orientation plays a role. Here, whatever I talked about grain direction, that is precisely the grain orientation. Okay.
Thank you, sir. Yeah.
Any other questions?
Yeah.
Sorry,
Yes,
Arunachalam, I could not hear you.
When there is a gap between two grain direction, the tendency of creating a crack will be higher, or
The tendency of creating what?
crack or failure what I'm talking
Yeah,
about.
so that is why grain boundaries are one of your weakest spots. Most of the failures in general initiate at the grain boundaries.
So we can orient this according to our needs.
Yes. So that is what people call it as a grain boundary engineering. By playing with the grain boundary, you can change the material properties. We will talk about it as well in the class. Yeah.
Okay.
Any other questions?
Sir,
Yeah.
in general, these categories, do you have any examples, sir, like metals or something?
I will talk about them. We are only talking about metals. You will have a copper, which is a polycrystalline copper. You can also have a single crystal copper. For example, single crystal materials are extremely useful when your turbine blades, for example. All turbine blades are usually made of single crystal materials. You can have same material, which is a single crystal counterpart, or it can also be appearing in polycrystalline form. A single crystal material is useful in some aspects, whereas a polycrystalline material will be useful in some other aspects. For example, if you take single crystal copper, it has a better conductivity than polycrystalline copper. But a polycrystalline copper is stronger than a single crystal copper. And if you want your material to have very high creep resistance, then you don't want to have grain boundaries, because grain boundaries are the ones which will create trouble at high temperatures. And hence, you want to avoid grain boundaries. That means it is better to have a material that is a single crystalline material. That is why turbine blades are usually made of single crystal materials.
Thank you, sir.
Yeah. Any other questions? Okay, if there are no further questions, I'll stop here and we'll see you tomorrow. Thank you.
Thank you, sir.
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 Thank you, sir.